Hi everyone. The first at-home lab you'll do has to do with refraction, specifically refraction of light. Refraction is a phenomenon that occurs with all waves, whether it be light waves, sound waves, surface waves on water, seismic waves, whatever. But it has to do with the fact that waves propagate at different speeds in different media of travel. So, for instance, when a water wave goes into shallower water, it moves at a slower rate. And in fact, the different wavelengths of water waves move at different speeds. But refraction occurs when a wave propagates from one medium to another and changes its speed. And we're going to look at refraction with light. So let's say this is one medium of travel, like air, and this is another medium of travel, like glass. And there's a change in direction. You've all seen this with refraction of light, like when you look into an aquarium or something, everything looks distorted because the light rays change direction as you go in there. And there's a quantitative theory that allows you to predict what that change will be. It has to do with what's called the index of refraction in the two media. So the index of refraction has to do with the wave speed. And so this is, c is the speed of light in empty space. It's about 300 million meters per second. And this is the speed of light in the material. This number is the index of refraction. So this is a measure of how fast the wave moves in different media. And so this is c over v2. Now the index of refraction for air is almost exactly 1. It's just barely greater than 1. Which means light travels barely slower in air than it does in empty space. But for glass, something like glass, the index of refraction is like 1.5. So light travels significantly slower in glass than it does in air. And that causes a change in the direction. You can talk about these two angles right here. You can predict from the index of refraction what the change in direction will be. In other words, given a theta 1 going in, you can derive the theta 2 as it's inside the material. And it's called Snell's law, and it looks like this. Now you'll be using this in the lab exercise, which is of course simulated transmission of light through different materials. This is about the only introduction you really need for the thing, but I'm going to derive this. There's a number of different ways to derive this, so if you want to watch on, you can see the derivation of this. The derivation includes calculus, which is beyond the scope of this course, but for those of you who are interested in seeing the derivation, I'm going to do this now. If you're not interested in seeing the derivation, go ahead and start the lab. Okay, so to derive this, again, there's a number of different ways to derive Snell's law. The one I'm going to use utilizes Fermat's principle. Fermat's principle is the path that a light beam takes to go from point A to point B is the path that minimizes the amount of time that it takes to get there. And wave phenomena all obey Fermat's principle. So you can imagine that if it's traveling faster out here and slower in here, it would take a little less time to go further in the faster medium than in the slower medium. And but if you go over here and then back, that might take more time. So what is the optimum path that you, and I can do a derivation that shows that this is true when the optimum path, the minimum time path, is taken. So let me just draw a couple other lines here. I'm going from point A to point B. Call this distance A and that B. Let's call this X. And then this whole distance L. Okay? And another thing you notice is that since these lines are parallel, this is theta 1 and that's theta 2. Okay, so I'm gonna do a derivation that utilizes some geometry here. Okay, so let's call this, sorry, this is D1 and that's D2. I've just named everything here. So if the velocity of light in this medium is V1, then the amount of time it takes to go from here to here is D1 over V1. And the amount of time it takes to go from here to here is D2 over V2, right? So the amount of time is D1 over V1 plus D2 over V2. And I'm just going to write D1 and D2 in terms of some of these other variables. So here I've got a right triangle. So D1 is the square root of a squared plus x squared. And D2 is the square root of b squared plus L minus x squared. So here's this is L, this is x, so this is L minus x. So L minus x squared plus b squared over b2. Okay, now one of the things that you learn to do in calculus is you can find optimizing things like this by taking the derivative of something and setting it to 0. Because if, let's say the time it takes is a function of x, and for small x it takes a lot of time, for large x it takes a lot of time, but for 1x the time is optimized. For that particular x the time is optimized. Well, the derivative of, so that shows the time as a function of x, and that's showing this curve. I don't know what the curve looks like, but it's probably something like this. And if you take the derivative, you find that the derivative is an equation for the slope of this. Where I find the slope is equal to 0, that's where x is optimized and t is minimized, right? Okay, so let's take the derivative of this. So dt dx is, let's see, this is 2x 1/2 times 2x over, I think that's right. And then this is, whoops, forgot my V1 here. And this is, so let's see, that's 1/2 times 2 times 10 minus 1 over V2. I hope I did that derivative correctly. Okay, then I set that to 0. So let's see, this 1/2 cancels the 2, that cancels that. When I take this to the left side, it's going to be negative, so it cancels that minus 1. So this is just x over v1 e squared plus x squared equals L minus x over v2 L minus x squared plus b squared. Now this looks kind of complicated to solve, but this right here is D1, so, and this right here is D2. And x over D1, this over D1, is the sine of this angle, right? So this is sine theta 1 over V1, and this is L minus x, that's D2, so that divided by that is the sine of that angle. So, and I'm nearly finished here because N1 is V1. If I solve for V1, solve this for V1, put it in here, I get N1 sine theta 1. And if I solve this for V2 and plug it in there, I get N2 sine theta 2. So there's Snell's law. So that's just Snell's law being shown to be true using Fermat's principle, the idea that a wave minimizes the time of travel to go from point A to point B, no matter what that is. And waves, all waves do that. Water, surface waves do that, sound waves, light waves. So there you have it.